Volume computation is something that I've bothered you before with periodically as we talked about definite integrals. Well, this is the presentation where hopefully all those seeds that we've planted will come to germination, will come to fruition, will bear us the fruit that we have worked for, because now we really want to make it stick. We want to make that step into the third dimension. So let us look one more time at what the idea is for computing three-dimensional volumes. The question is, well, how do we compute volumes of irregularly shaped three-dimensional objects? Such as this one, for example, and note that I am also not implicitly assuming that maybe this cross-section is a circle or so. This could be an ellipse or something more complicated. So how do we do that? Well, what did we do for areas? For areas, we used rectangles instead of complicated shapes, and I think here I have to convince my computer that this is a trustworthy document. But for areas, even though the area underneath this quadratic certainly has an irregular shape, we used rectangles, and as we use more and more rectangles, we got a better and better approximation for the area. Well, that is something that ought to work in 3 dimensions also. The 3-dimensional analog of a rectangle is a cylinder, and cylinders have an easy volume formula, right? You've got a base, you've got a height, and you've got a top element there, a top area there, and so basically now you've got base area B, a height h, and then the volume is just volume equals base times height. And note again that a cylinder doesn't have to be something that has a round base or a square base or anything else. A cylinder could have a puddle as its base, and as long as it's got vertical sides in mathematics, we would consider it a cylinder. Okay, so that should work, I say, because if we're looking at this irregularly shaped object here, if we approximate that with cylinders as we're seeing over here, and might as well stop it right here, we can certainly see here that this object is not the same as this object. They still have different volumes, but because the cylinders, these steps in these cylinders are sufficiently small, the objects already look very, very similar, just like the area that was covered by the rectangles in a Riemann sum and the area that was actually trapped by the function between the function and the x-axis started looking very similar. And so as we use more and more cylinders, as we're making a finer and finer approximation, it seems that we should be able to approximate 3-dimensional volumes through volumes of cylinders. Let's let this run its course one more time. And okay, so now how do we formalize that? Well, basically we take an object, and the idea is we're going to align it along an axis. And if this thing is standing up, the axis is going to be the y-axis. That's one way to visualize it. We will also have the theorem where we align the object with an x-axis in case the thing is fallen on its side or so. But we find ourselves an axis so that vertical to this axis we have nice cross-sections for which we have a good formula. So then along this axis, the object goes from here y equals bottom b to y equals t for top. And we cut the object into little slices, right? What we have seen in the animation on the previous panel was that we've got a bunch of slices. Well, let's not just take a look at one representative slice. That slice has a thickness delta y because we're going along the y-axis, and it has a base area, which is the area of the cross-section at height y. That would be the area A of y. And the idea then is that the total volume is the sum over all the volumes of these little slices, and of course the heights of these slices are the delta y's that we have, and the areas of the bases are the areas at every single yk where every slice starts as we slice this thing along the y-axis. So then the volume approximately is equal to the sum, and as we let n go to infinity, as we let delta y go to 0, the approximate equality becomes an exact inequality, and we get that the volume is the limit as n goes to infinity, k equals 1 to n a of yk delta y, which is the integral from the bottom to the top of a of y dy. And so that's the theorem. The volume of a given solid is the integral of the cross-sectional areas a of y from bottom to top. Symbolically, v equals integral from b to t a of y dy. There's a period missing. And so I should fix that period. Okay, we have the period. And so the integral is just v equals integral from bottom to top a of y dy. And that's exactly what we had in this picture, right? Basically, we're integrating from the bottom to the top, and we're looking at all these slices, and all these slices have volume base area times height a of y times dy. And if we want to visualize the whole thing with the object being aligned on the x-axis, well, it's basically the same thing. The volume of a given solid is the integral of the cross-sectional area as a of x from left to right. Symbolically, that would be the volume is the integral from L to R a of x dx. And that's if we have an object where the cross-sections that are perpendicular to the x-axis are easier to compute than the cross-sections that are perpendicular to the y-axis. Well, then we would say that the object goes from x equals L for left to x equals R for right, and that's the bounds for the integral. And now we're having vertical slices, and again it's the same thing. This time the base stands vertically, but the base area would be a of x, the cross-section area at slicing at x, and the thickness is delta x, so we end up with integrating or summing a of x dx's. Okay, how does that work? Well, the algorithm is therefore fairly simple to compute volumes with areas. First of all, we choose an axis through the object so that the areas of cross-sections perpendicular to the axis are easy to compute. And that may mean that they have an easy shape, or that may mean that they behave nicely. Meaning that you've got a nice function that tells you what the radius or side lengths of your cross-sections are. You make the chosen axis either the x-axis or the y-axis. I mean, you can just keep the object aligned as you visualize it, and then make the axis the x-axis or the y-axis, or you could mentally also rotate the object in your mind and make the axis then the axis that you're more comfortable with. You compute the area a of y or a of x of the cross-section at y/x. You obtain the lowest and highest projections b and t onto the y-axis, or the leftmost and rightmost endpoints L and R onto the x-axis. And you set up and compute the integral from bottom to top a of y dy if you go along the y-axis, or the integral from left to right a of x dx if you go along the x-axis. Now notice that once you're past set up, the problem is essentially done. And I'm going to harp on that a little bit because we want to keep our mind structured. The modeling is the visualization. The modeling is the creative part. The modeling in many ways is the hard part in this problem. Computing integrals, well, we know how to do that. Okay, that doesn't mean it's trivial. Some of these integrals can get very tedious. In fact, I can probably for the homework set up some integrals that are specifically designed to lead to integrals that make you review your integration methods. But computing integrals is a separate skill, and computing integrals also is something that, if worst comes to worst, if you just are ultimately on the job and have to compute the volume of a really ugly object, you can always let a computer do that. So the setup, that's really the new stuff that we're doing here. And here we go, that is the algorithm. Let's take a look at how that works. So I want us to compute the volume that is obtained by rotating the graph of f of x equals x squared minus 1 about the x-axis between -2 and 2. What does that look like? Well, that is a solid of revolution. And so, as I have to explain to my computer again that I'm trustworthy, this is a solid of revolution. What do we do here? We take the graph f of x equals x squared minus 1. That's the graph. Going from -2 to 2. And so the x-axis is sitting here in space. And we are rotating our graph around that axis. And so we're getting this thing that sort of looks like a piece of wrapped hard candy. And you can see I went a little bit too far here. Let's rotate that all the way around. So that is a solid of revolution. Now, for the volume of a solid of revolution, there is actually a direct formula where as soon as you know what f of x is, you just set up the formula, compute the integral. But that's not even a golden parachute, that's a lead parachute. Because what you want to be able to do in volume computations you want to be able to visualize what the volume looks like, because this is a preparation for multivariable calculus and for working in real life. Remember, real life is 3D, so you want to be able to visualize three-dimensional objects. You want to be able to visualize cross sections of three-dimensional objects, and so on and so on. And so in this presentation, as well as if you're using it my book, I didn't put that formula front and center. I'm always going to say we will visualize the object, we're going to find what the cross sections are, we're going to find the areas of the cross sections, and then we're going to integrate. That takes a little bit longer, but as we are going to see when we're looking at the frustrum of a square pyramid, which is I think the next example, that in that fashion we are used to visualizing, and we can therefore also work things out that are not solids of revolution. That being said, let's move on. So what do we have? Axis and coordinate system. Well, this thing is rotating around the x-axis, so we probably want to use the x-axis because that's where we know that the cross sections are circles. The area of the cross section therefore is pi r squared, and the radius, well, the radius is the value of the function at x, right? So the area of the cross section is pi times x squared minus 1 quantity squared. And the bounds, well, the bounds were given, goes from -2 to 2. And so now, unlike for areas, quick note here, negative radii don't really matter because we're squaring stuff here. For other area formulas, we may have to take care of negative signs, but for solids of revolution, we don't have to worry about that. And so what we get is that the volume is the integral from the left to the right, from -2 to 2, of pi times r squared, pi times x squared minus 1 quantity squared, and that's exactly this x squared minus 1 here, dx, which is the little thickness. And again, this is the setup. As I said when we were looking at the algorithm, here is where in some ways the problem is done, because from here on out it's just computation. That doesn't mean the computation is trivial, even though this one isn't going to be too bad. But this is also the point where in a physics class sometimes the professor says the rest is just math. It may well be, but it's going to take a while. It's not like somebody says, oh, you just simplify and in one step where you're adding two fractions or so you're done, as sometimes may have happened in algebra class. The steps that are being left out in advanced classes are often more numerous and more complicated than what we have seen before. And so being aware of that can help you a great deal. Nonetheless, let's work it out. Well, the pi is common, so we factor it out. We square out, we work out the square, so that's x to the 4th plus or minus 2 times x squared times 1, so 2x squared plus 1 squared, so plus 1. And that's a straightforward integral, right? I mean, the antiderivative, okay, keep the pi out front. Antiderivative of x to the 4th is 1/5 x to the 5th. Antiderivative of 2x squared is 2/3 x cubed. And the antiderivative of 1 is x, and we go from -2 to 2. We're plugging in the numbers, so let's see, we would get pi times 32 over 5 minus 16 over 3 plus 2, and then the same thing at the lower bound with different negative signs, right? 32 over 5 minus 16 over 3 plus 2 minus, and now here, because we're plugging in -2, we get -32 over 5 plus 16 over 3, and that x cubed should be gone. Minus 2, I shall eradicate the x cubed. Okay, so now the x cubed is gone. And, well, so now what do we get? We get 64 over 5, we get 32 over 3, and we get 4. 64 over 5, 32 over 3, and 4. And then, well, we can just do a lot of really ugly mental arithmetic. Let's see if we can work this out. But ultimately, I mean, we can use a calculator for that too. Let's see, common denominator would be 15. Well, that doesn't sound too promising. But nonetheless, 64 times 3 would be 192. And 32 times 5 is 160. So we end up with 32 over 15. Should be plus 60 over 15, 92 over 15. Well, here we got it worked out, 92 over 15, and we've got the pi at the end. Hey, I got that right. Well, that's really cool, but as you can see, just as I said the problem is done right here, we could have said the problem is done right here because the rest is just numbers. We still have to get it right, and it's good practice to do this mental arithmetic as well as the integrals. But what we're learning new here is all in the setup. Now, the interesting thing about solids of revolution is that solids of revolution are real. I mean, this is a picture of a lathe, a turning machine as they're also called. And basically what you've got there is typically you have some mechanism here to hold a metal bar in place. And then this motor over here, well, it's really hard to see, but the motor is over here on the left, turns the whole thing really fast. And then you've got this cutting tool here, which you can move along the metal bar and make any kind of shape that is rotationally symmetric. So that means all sorts of turn components, as these things are called, ultimately are solids of revolution. So this is not just an invention of mathematicians. Anytime you see something that is rotationally symmetric, if it's a metal part, there's a good chance that you're looking at a turn component, especially when it's solid. Okay, well, like I said, however, not all the cross-sections are round. So the next thing I'd like us to do is I'd like us to compute the volume of a frustrum of a square pyramid with base length 4, height 1, so that the side length at the top is 2. And especially in the English language, first thing that you realize is what on earth is a frustrum? Well, a frustrum is a pyramid where somebody cut the top off. So the frustrum of a square pyramid looks like this. A square pyramid has a square base, and then everything goes up to that top point somewhere, and in a frustrum, you've cut off the top, and so that means if your base area is a square, then your top is also a square. So this is more like something that you may have seen also in archaeological pictures of Mayan pyramids, I think specifically, where often they didn't do a pyramid all the way to the apex, but just set up a pyramid shape that had an area on top where they could perform their various rituals. So that's what a frustrum of a pyramid is, especially for a pyramid with a square base. With a round base, of course, it would be a round base on the bottom and a round area on the top. And what do we know now? We know that the side length on the bottom is 4. We know that the side length at the top is 2. What else do we know about this thing? Well, the cross-sections, if we slice vertically, the cross-sections are rectangles, but we've got rectangles getting larger. We've got well, actually, the cross-sections aren't even rectangles. The cross-sections are trapezoids. I think trapezoids. Basically, long side on the bottom, shorter side on the top. So those cross-sections would be really hard to compute, not to mention the cross-sections would get larger, would stay the same, and then would get smaller again. Whereas if we slice horizontally, we get square cross-sections. That's what I meant when I talked in the initial algorithm about finding an axis for which the cross-sections are basically for which the cross-sections cooperate. It is a lot easier to model this thing with horizontal cross-sections because you've got squares when you cut horizontally. In order to set that up now, well, height is 1. In order to set that up, we better look at a vertical cross-section. And okay, pardon my language, I think that's what people call a trapezoid. Right now, I'm not quite sure about that. Yeah, that comes from being a foreigner, sorry. But that's a vertical cross-section. And so now we know that the actual cross-sections are squares that are going into the plane that is defined by this panel here. And we need to know what the side lengths of these squares are. All right, well, let's put a coordinate system in there. Here's the x-axis, here's the y-axis. We know the height is 1. We know that if the bottom side length is 4, then that means this goes from -2 to 2, because I wanted the y-axis to go through the center. And that means that this here is -1 and this here is at 1. And so now we need to, I guess here I should have had a pause in there, but now what we need to know is this slanted side on the right of the cross-section. Well, we know that that goes through the points 1, 1 and 2, 0, and that means we can figure out the slope. The slope is 0 minus 1, right here, over 2 minus 1, which is here. So the slope of that thing is -1, and that means that the equation is y equals -x plus 2. We know it's got to have slope -1, so it's got to have a -x. And at 2, this y is equal to 0, so okay, -2 plus 2 would be 0. That means we have a line here that has the right slope, and that goes through the point 2, 0, so this is the equation. Okay, however, we need the equation as x in terms of y, because what we're interested in is, of course, the horizontal cross-section. So that means we solve and we realize that x is equal to 2 minus y. And that gives us the radius of these square cross-sections. Well, the side length is what we actually need. So the side length at height y would be 2x equals 4 minus 2y. We just double this equation here, right? Because you just don't work with the radius of a square that much. And well, so that means that the area of the cross-section at height y is 4 minus 2y quantity squared. And if we now set things up, then the volume is the integral from 0 to 1, from the bottom to the top, of the areas of the cross-sections dy. And again, technically the setup is done, the rest is quote-unquote just computation. Of course, again, the integral isn't that bad. However, I have to admit to you that before I started recording this presentation, I was correcting the slides and actually got that one wrong a couple of times. That's not something that you want to do, but it is just something that can happen. So do not shortchange your computation. Sometimes on an exam, or also when you're doing other computation, once you've got this, you breathe a sigh of relief because the hard part is over. Well, just because the hard part is over doesn't mean that we can mess up on the rest, right? Okay, now the computation, you know already. Well, we keep the integral, we multiply out the parentheses, 16 minus 16y plus 4y squared, right? 4 squared minus 2 times 2 times 4 times 2, which is the 16 times y, and then 2y quantity squared is 4y squared. And so we integrate that. Integral of 16 is 16y. Integral of 16y is 16 halves y squared, which ends up being 8y squared, and we keep the negative sign, of course. Plus, and the integral of 4y squared is 4 times 1/3 y cubed, which is here. And we go in the boundaries from 0 to 1. And, well, that at the upper bound gives us 16 minus 8 plus 4/3, and at the lower bound we subtract a bunch of zeros. So that's 8 plus 4/3, that's 24/3, plus 4/3, that's 28/3, and that's already it. Okay, now something else we can do is, of course, we can work with parameters, and I'd like us to derive a really neat formula here where we're looking at a sphere of radius a, and we want to derive the formula for the volume of a cap of height h. So if this is our sphere, what we're actually interested in is just the volume of one of these bottom caps. This is the kind of thing that you have when, say, you've got a spherical tank for a liquid. Well, then the liquid will, of course, as long as there is gravity, which we would hope as long as you're on Earth, the liquid would be in the bottom of the spherical tank and would cover exactly this volume here, and for that you have a certain height h, and the shape is the cap of a sphere of radius r, radius of your tank, and the height is h, the height of the liquid inside your tank there. Okay, so how do you work that out? Well, we look at a cross section and we put axes along there, x and y, and we know that x squared plus y squared equals r squared. We will be interested in the radius of these cross sections because, again, we're going to slice along the y-axis, right? If we were to slice along the x-axis, we would get these parts of circles for which we don't really know what the area is. So we want x in terms of y, and the radius of our cross sections will be x. And so x squared plus y squared equals r squared gives us that x is equal to the square root of r squared minus y squared. And the left side is, of course, that x is negative square root r squared minus y squared. The thing goes from negative r to negative r plus h because we're looking from the bottom to a height h. The cap, the volume at the bottom now is just this part of a circle. And so now a cross section at height y would have area pi times x squared. And we know that x is square root r squared minus y squared. So the area will be pi times square root r squared minus y squared squared. And when you square that out, you get pi times r squared minus y squared like that. And so that means that now, if we integrate from the bottom to the top, cross-sectional area dy, the integral will go from negative r to negative r plus h, because it's supposed to have height h, pi times r squared minus y squared dy. And again, here is technically where the modeling is done. The rest is just solving an integral, which of course now is a little bit more demanding because we have to deal with the parameters, but we can do it. So we find the antiderivative. We keep the pi on the outside. The antiderivative of r squared with respect to dy, well, r squared is a constant, right? So it's just r squared y. And the antiderivative of y squared is, of course, 1/3 y cubed in the bounds from negative r to negative r plus h. From here on out, it's now just some ugly algebra. We plug everything in, and you just want to do that step by step. So we keep the pi on the outside, have a big set of parentheses. We plug in negative r plus h for y. We plug in negative r plus h for y. We plug in negative r for y. And we plug in negative r for y here. And now we just start simplifying. And so we would get pi times negative r cubed plus r squared h right here. Then we have to work out a cube. Let's see. So negative r plus h quantity cubed gives us a negative r cubed with the 1/3, and the extra negative sign gives us a plus 1/3 r cubed. Then we get 3r squared h times 1/3, and the negative sign gives us negative r squared h. Then we get minus 3 times negative r times h squared. Double negative gives us a plus. The 3 and the 1/3 goes away, so we get rh squared. And then we get h cubed as the last term, times 1 times negative 1/3 gives us negative 1/3 h cubed. That certainly is something where you want to just get some paper and pencil and just work that out for yourself. And, well, the last parenthesis, negative r cubed is plus r cubed. And here we get 1/3 r cubed, and we get negative, which gives us negative 1/3 r cubed. Now we combine all that, and what do we get? We get that the negative r cubed and the r cubed goes away, the 1/3 r cubed and the negative 1/3 r cubed goes away, so there's no r cubes. We've got an r squared h and a minus r squared h, so that goes away. And that means we're just left with rh squared minus 1/3 h cubed, and of course we've got the pi out front. So that's pi rh squared minus 1/3 hr cubed, 1/3 h cubed. And if we factor out an h squared, we end up with pi h squared r minus h thirds. And that is the formula for the volume of a cap of height h of a sphere of radius a, of radius r. Quick sanity check. We know that the volume of a sphere is 4/3 pi r cubed. And for the whole sphere, well, a sphere is a cap of itself, except that the height is 2r, right? You've got a height of r to get from the bottom to the halfway point, and then another height of r to go all the way to the top. So when h is equal to 2r, this ought to be the volume of a sphere. And, well, r minus 2r divided by 3 is r thirds, and 2r squared is, 2r quantity squared is 4r squared, so we would end up with pi times 4r squared times 1/3 r, which is exactly 4/3 pi r cubed. So if you use the formula from geometry for the volume of a sphere as a reference point, then this is a sanity check that this has a good chance to be right. If you want to look at it the other way and say that we have just derived all these formulas, then in particular, we have also derived the formula for the volume of a sphere of radius r. And one final word here, and this is something that we're going to look at also in more detail as we do more modeling, and that is that working with these Riemann sums is a bit cumbersome because you have to look at the deltas. You have to take the limit as n goes to infinity and all that. And what we have seen here is, because we had this theorem that said just find out the cross sections and then multiply with dy, let's see if we can formulate that in such a way that also in the future we can set up integrals a little bit more directly. So let's look one more time at our volume. We find ourselves an axis from the bottom to the top of the element so that we've got nice cross sections. We're looking at a cross section, and rather than saying that the thickness is a finite delta, the way Leibniz would have looked at this is he would have said that this volume, this cross section here is a differential or an infinitesimal thickness, and an infinitesimal is a very sophisticated mathematical object, and it took until the 1960s until people could actually justify these things formally correctly, but basically it is something that is shorter than any real number, so we really couldn't see it. So this is way overblown here, but we have a differential thickness dy. Then we take a cross section, a of y, and so then the volume, of course, if every slice has differential thickness dy and area a of y, then if we sum continuously, and to Leibniz and to a lot of extremely good 18th and 19th century mathematicians, an integral was just a continuous sum. If we sum continuously to get the volume, we basically end up with the volume being the continuous sum from the bottom to the top of the differential volume of one of these differential cylinders, where the cylinder has a differential height dy and a macroscopic cross-section a of y. So in this fashion, we can potentially shortcut dealing with all those little deltas. That is something that physicists are very much adept with. This is the kind of thing that you can also see in mechanics texts and electrodynamics texts and so on. And there are two ways to look at that. With standard mathematics, infinitesimals cannot be justified, and so then setting up Riemann sums is probably the right thing to do, and setting up Riemann sums definitely is the right thing to do when the only chance you have is numerical analysis. However, for the conceptual derivation and for just setting up the integrals, which then later on could be computed with Riemann sums by a machine, these differentials work very nicely. So if for your modeling you want to think of your integral as a continuous sum, then the integral sign will always take the place of the summation in the Riemann sum, as we have also seen. The dy is a differential thickness, a differential step, and your integrand is whatever your differential step has to be multiplied with. With that, first thing for you to do is to solve some volume problems to make sure you get the three-dimensional visualization. We're going to keep messing with differentials as we're discussing work and various other things, and I think for a while I'll actually try to explain it with Riemann sums as well as with differentials, because both ways are good ways to explain things, and as long as at least one of them works for you, you will be able to proceed. Alright, well, that was a lot of concepts, a lot of visualizations. As I said, this time you've got to make it count, so knock those volume problems out. I'll see you next time.